how many numbers would you need to describe the Moon? To begin with, it's pockmarked with a wide variety of craters from different asteroid impacts over billions of years. A similar exomoon orbiting a similar exo-Earth in a different solar system, even if superficially alike, would have a completely different pattern of asteroid impacts. To characterize each precisely, at a minimum, we would need to give two coordinates, latitude and longitude, for every one of the thousands of craters along with the size of each crater. Very rapidly, we find ourselves needing thousands of numbers to describe a moon, even before we start talking about the chemical composition of the moon's surface and how that varies in different regions. The number of numbers we need quickly expands from thousands to millions and beyond. And that is just a moon, one of the comparatively more simple objects in the cosmos. How many more numbers would it take to describe a planet, a star, a nebula? Or indeed, how many numbers would it take to describe the most massive single object in the entire universe? A black hole. The answer for these monsters may surprise you. 3. 3 numbers, and no more. No matter how heavy they are, no matter where they were formed, no matter whether they are in our own Milky Way galaxy or a billion light-years away, 3 numbers, and only 3, are sufficient to define them completely. On the one hand, this makes black holes seem like very simple objects. Only 3 parameters are necessary to classify them: their mass, electric charge, and angular momentum. Know these 3 numbers and you have everything. And yet, there are an enormous number of ways to form a black hole. They can be formed by gradually swallowing up gas and dust over billions of years. They can be formed by the direct collapse of a massive star in a Type II supernova. Perhaps yet another could grow through repeated mergers of other black hole pairs. We could even imagine a hypothetical black hole formed from the contents of every encyclopedia and every electronic databank of every civilization in the galaxy, every piece of information and every single number ever thought or said by anyone, ever. Anything and everything in the universe can go into a black hole, and yet, once it is formed, all of that information is reduced to 3 numbers. How the black hole was made and what went into it becomes almost irrelevant. And so the question is, given this almost uncountably large number of possibilities for making a black hole, how can they then be described by just 3 numbers? Where has all the other information gone? Has the black hole forgotten about its origins, or does this information survive in some hidden form? Just what is inside a black hole? And what could it mean for the rest of the universe? Many of the atoms that make up who you are can actually be traced back to the very first second of the Big Bang, 13.8 billion years ago. It is fascinating to trace our true origins. And that's why MyHeritage is such a fun service to sign up for, our sponsor today. MyHeritage makes it fun and easy to build your family tree and discover your origins, and you might also find new relatives. My family is a mix from all across the British Isles. But I was still surprised, for as soon as I typed in my father and mother's name and birth dates into their amazing smart match system, it connected my family tree with someone in Australia, which revealed waves of relatives I never even knew about. So within about 5 seconds of logging on, my family tree already had 72 people. And as well as this, I matched with someone on my father's side that opened up whole new branches of cousins in the USA. My family was more widespread than I thought. And this was possible because MyHeritage is a worldwide leading family history service, and they have more than 20 billion records available. Indeed, here is an image of my great-great-grandfather I'd never seen before. And as a bonus, you can even enhance and colorize old photos like these to bring your family back to life. So sign up for a 14-day free trial and enjoy all the amazing features MyHeritage has to offer. Thanks to MyHeritage for supporting educational content on YouTube. In the 1780s, the position of a country priest in the Church of England was not especially demanding. A large house with a decent income, a group of servants to do the household chores, and younger curates to take services and visit the sick. To those who wanted it, a lazy life of leisure was on offer. But to those who wanted something more, there was time to think deeply about the world around them. And this is how English parson John Mitchell spent his time. By the 1780s, Mitchell had a pretty good idea of how gravity worked. A century earlier, Isaac Newton's theory of universal gravitation had shocked the scientific world. Gravity, Newton argued, was a universal force. Anything that had mass gravitated, pulled instantaneously on everything else. Nothing could avoid the force of gravity, not even, Mitchell mused, light itself. For as well as thinking about gravity, Newton had also argued that light consisted of tiny individual particles, little atoms of light, which we would now call photons. If this theory of light as particles were true, and gravity was universal, then gravity should be acting on these tiny particles of light, tugging at them and pulling them back. And Mitchell also knew that light travelled fast. Very, very fast. Indeed, earlier in the 18th century, the astronomer James Bradley had measured the speed of light, and measured it well and accurately through thinking about the aberration of light from distant stars. As the Earth moves through its orbit, the vector combination of the velocity of the Earth and the velocity of light changes, just a tiny amount, but enough to change, very slightly, the apparent location of stars in the sky. Through this, the speed of light was known to be around 180,000 miles per second. This was fast, but not infinite. And finally, intuitively, Mitchell knew that an object thrown upwards would fall back down. But if thrown upwards fast enough, this does not happen. Instead, it has enough speed to escape the Earth's gravity and reach space. The threshold value, known as the escape velocity, is the minimal speed of vertical launch required to escape a planet's gravity and reach infinite space. It's an easy calculation in Newton's theory of gravity to work out this escape velocity for any given planet and how it depends on the size and density of the object. The more massive the object and the more dense it is, the bigger the escape velocity. For example, for the Moon, this escape velocity is around 2.4 kilometers per second. For the Earth, this becomes around 11.2 kilometers per second. For Jupiter, just under 60 kilometers per second. And for our own Sun, roughly 617 kilometers per second. But imagine an even denser body. What about a body, thought Mitchell, which was sufficiently dense that its escape velocity exceeded the speed of light? For such a body, light emitted from the surface would not be able to escape. In this case, such a body would appear as gravitationally massive but entirely dark, trapping even light under the pull of its gravity. The language and argument here is that of Newtonian physics that would be replaced by Einstein's theories, but the concept it is describing lives on and is clearly recognizable. And Mitchell's work was, although the actual name would not be used for almost 2 centuries, the first description of what we now call a black hole. But Mitchell was way ahead of his time, and his result seemed no more than an abstract curiosity. It therefore went into the scientific back drawer, and stayed there for 150 years. And the next time this drawer would be opened would be in the miserable trenches of the First World War, where the German astronomer Karl Schwarzschild, desperate for an escape from the hell surrounding him, pondered the equations of Einstein's brand new theory of general relativity. Having developed the special theory of relativity in 1905, 10 years later Einstein succeeded in extending it to include gravity, constructing his general theory of relativity. This theory requires 10 equations to describe it, but when first written down they looked formidable and almost impossible to solve. And so in trying to solve them, Schwarzschild looked for the simplest possible solution he could imagine, a spherically symmetric spacetime around a concentrated point-like mass. Plugging everything in and calculating carefully, he obtained a solution, now known as the Schwarzschild solution, probably the most famous solution of Einstein's equations. Schwarzschild's solution involves one parameter, a uniform spherical mass. In general relativity, mass deforms the nearby spacetime. The magnitude of this deformation depends on the radial coordinate. The closer to the mass, the bigger the deformation, while far away, there is little change. And the Schwarzschild solution had one deep and striking property visible in it. There was a critical distance from the mass where something strange happened. Some terms in the solution appeared to go to zero, while others went to infinity. What did this mean? Although it was not possible to go through the full mathematical derivation, these zeros and infinities at a critical radius, known as the Schwarzschild radius, indicated the presence of an event horizon for the black hole solution, a spherical shell at a certain distance from the center of the black hole that represented a point of no return for objects coming in from far away. No object can move faster than the speed of light. Outside the horizon, an object moving at the speed of light away from the black hole can escape its gravitational pull. But any closer to the black hole than the event horizon, there could be no escape, not even for light. The laws of physics themselves forbade any escape. Any astronaut that crosses the black hole event horizon finds themselves on a one-way passage towards the center of the black hole. Once inside the event horizon, time always points towards the very center of the black hole. As the astronaut falls further in, the pull of gravity becomes stronger and stronger, and so they continue falling until they reach the singularity itself, a place where the laws of classical general relativity break down and the curvature of space-time becomes formally infinite. This was similar to Mitchell's calculation of a radius where the escape velocity exceeded the speed of light. If a certain mass was condensed into a radius smaller than its Schwarzschild radius, it would collapse inescapably. The Schwarzschild radius for our Sun is around 3 kilometers, and for the Earth it is less than a centimeter. A human Schwarzschild radius is on the order of 10 to the power of minus 23, smaller than the nucleus of an atom. And if all the stars and gas and dust within the Milky Way were somehow condensed into a radius less than 0.2 light-years, a truly mammoth black hole would eventually form. Schwarzschild solution was found in 1915, but as with Mitchell's work, for half a century seemed merely an intellectual curiosity. Did it mean anything physical, or was it simply a mathematical artifact? Unfortunately for the study of black holes, as quantum mechanics revolutionized one branch of physics after another throughout the 1920s, 30s and 40s, gravity and general relativity were viewed very much as a backwater. The comments of American physicist Richard Feynman on a conference on gravity he attended in the early 1960s give an idea of what people thought about it. I'm not getting anything out of this meeting. I'm learning nothing. Because there are no experiments, this field is not an active one, so few of the best men are doing work in it. The result is that there are hosts of dopes here, and it's not good for my blood pressure. But the state of the field described in Feynman's caustic summary would all change in the late 1960s as a combination of theoretical and observational breakthroughs brought research into black holes and general relativity back with a vengeance. And this has remained the case to the present day. And in the public mind, there is one scientist more than any other associated with this renaissance. Among the icons of 20th century physics, Stephen Hawking holds a privileged place. His remarkable life story has inspired millions. Born in 1942, he studied undergraduate physics at Oxford before moving to Cambridge to do a PhD. But during his doctorate, Hawking's life changed drastically in two connected ways. First, at the age of 21, he was diagnosed with a degenerative muscle-wasting motor neuron disease, which had a typical life expectancy from diagnosis of around 18 months. And second, having coasted to a first-class honours degree at Oxford, for the first time in his life, he started working hard and with intensity. As the prospect of early death loomed, he threw himself into his work with a desire to achieve something and leave a legacy of his talent. Of course, Hawking would end up outliving anyone else with the disease, eventually dying in 2018 at the age of 76 as one of the most celebrated and famous scientists in the world. And the scientific reasons for this fame came from the first black hole renaissance. mostly occurring in the years from 1967 to 1974, in which a period of extraordinary collaborative creativity between Hawking and the mathematician Roger Penrose upturned the stale subject of general relativity. Together, Hawking and Penrose proved a set of key theorems. If you start with a group of heavy particles close together and pulling on each other under gravity, it is not intuitively clear what will happen. Perhaps they will collapse and form a black hole, but perhaps they will also slingshot off each other and escape. Hawking and Penrose resolved this question. They showed that under quite general conditions, collections of matter particles under gravity would collapse, and that the inescapable endpoint of that collapse would be a singularity in the fabric of space-time, surrounded by a black hole. This result was not about intuition or hope or expectation. It was a proof. This Hawking-Penrose collaboration also changed how relativists thought about space and time through a novel conceptual visualization called Penrose diagrams. These simplified much of the complexity of many solutions to Einstein's equation. Suddenly, it was possible to have a simple and complete global view of what could affect what when thinking about black holes, a clear diagram to illustrate the causal structure of space-time. In these diagrams, light always traveled at 45 degrees, making it possible to see easily which points in space-time could causally affect which other points. In this language, the horizon could be viewed as the crossover, where there can no longer be any causal contact with space infinitely far away. As his body wasted away, Hawking's mind soared and his imagination stretched across space and time. There was good reason to think that the fanciful objects described by these squiggles on the page, black holes, really could exist in the galaxy. And luckily, at the same time, the quality of astronomical telescopes was improving rapidly. As satellites became capable of launching telescopes into space, for the first time the sky could be observed above the clouds, and not just in optical light, but also in other wavebands, such as X-rays. And it was this that led to a shock. The X-ray sky was far busier and crowded than expected. In fact, there was one source that was especially bright and compact, known as Cygnus X1. Where were so many energetic X-rays coming from? How could they arise from so small a region? There was only one good candidate to explain the data: the presence of a compact black hole, with the energetic X-rays given off as matter was accelerated, falling into it. Since the first discovery of Cygnus X1 as a black hole in the 1970s, many more have been discovered. There may be as many as 100 million black holes in our own galaxy alone, and in 2015, colliding black holes were first observed, as the gravitational waves emitted from their collision were picked up by the LIGO Observatory in the United States. But the excitement about black holes in this period did not come only from astrophysical observations of the galaxy. In offices and on blackboards, in long equations furiously written down in late-night bursts of creativity, the theoretical exploration of them became a bizarre new playground for the most extreme questions in the cosmos. Nothing is more familiar to us than the human face. While easy to recognize their basic shape, they come with an almost infinite variability. Age, complexion, hair shade and style, freckles and moles, the smiles, the teeth, the skin freshness. How many numbers and how much information would you need to specify any human face completely? A lot. Something much less familiar, and apparently more exotic, is a black hole. And yet in a way, they are far, far simpler. And that was reflected in the solutions to Einstein's equations. Despite this, it was not easy to find these solutions. Soon after Schwarzschild's 1915 discovery of the simplest black hole solution, another generalization was uncovered: an electrically charged black hole, the Reissner-Nordström solution. But it was not until almost 50 years later, in 1963, that the most important generalization of the Schwarzschild solution appeared. This was the Kerr solution, named after the New Zealander relativist Roy Kerr. Like the Schwarzschild solution, this also described an uncharged black hole, but this was one with angular momentum, or spin, a black hole spinning on its own axis. Think of a supermassive ballerina, rapidly spinning, extremely heavy, arms stretched out. This cosmic ballerina is heavy enough to be almost, but not quite, at the threshold density to form a black hole. As she brings her arms in to increase her rotational speed, she passes this threshold density and immediately collapses to a black hole. But this is a spinning black hole. The angular momentum she had prior to the collapse has not disappeared. It has gone into the black hole, and this is reflected in the Kerr solution. But why did there seem to be so few black hole solutions? Only the Schwarzschild solution, the Kerr solution, and their generalizations to include electric charge. Indeed, this limited number was not through lack of effort, for as physicists studied the equations of general relativity and thought about what type of solutions led to black holes, they first suspected and then later proved something distinctive about these black hole solutions, a result now known as the black hole uniqueness theorem, with remarkable implications. Most astronomical objects have an almost infinite number of individual characteristics. Quasars are vast cosmic engines. Through the brutal friction and temperatures created by their central black hole, they form a superpowered dynamo. Trillions upon trillions of numbers would be needed to successfully describe and recreate an even vaguely similar object. Stars, though superficially much more straightforward, come in almost endless variety and evolve dramatically through their lifetime. From the supermassive first stars, living for only a few millions of years at the beginning of the universe, to the ultra-low-mass, frozen stars expected to linger on into its twilight, they are a bounty of possibility. Even something as simple as a sub-kilometer asteroid has its foibles and birthmarks, pocked by millennia of travel through interplanetary space. But for black holes, this turned out not to be true. The allowed solutions for black holes were tightly constrained and, in fact, completely and totally characterized by 3 properties and 3 numbers. To describe a black hole, it was proved you needed only a mass, an electric charge, and an angular momentum. And that was it. That was all. Nothing else. No more parameters existed. 3 numbers gave you everything. As the American physicist John Wheeler neatly summarized, black holes have no hair. And so every black hole in the universe could be classified in terms of its mass, its charge, and its spin, and nothing more. Yet behind the mask of the horizon, there are an almost infinite number of ways that a black hole could have been formed. And so how do all these starting possibilities end up as just 3 numbers? Let me count the ways. When a physicist hears these words, they immediately feel connected to an apparently totally different part of physics, that of thermodynamics, the science of heat, temperature, and entropy. Imagine you were sat in an aeroplane. The cabin you are in is filled with air, gas at a certain temperature and pressure. We can feel both properties. We sense hot or cold blasts of air, and likewise feel in our ears the change in cabin pressure when the aeroplane descends. Yet we don't feel the individual atoms that make up this gas. Within the gas, filling any space, an almost uncountably large, but still finite, number of molecules bounce into and off each other. So many that ponderous great lumps of flesh, such as ourselves, cannot resolve the individual atoms. When we talk about a conservatory on a hot summer's day, we say simply that it is hot. We do not say that the gas molecules in it are moving faster, even if we are dimly aware that underneath the concept of heat lies a micro-description in terms of atoms moving faster and carrying more energy. And so gases, have temperature and pressure. Black holes have mass, spin, and charge. For both physical systems, we characterize them with a few numbers. For both physical systems, these numbers hide an internal cornucopia of states, arrangements, and possibilities. And there is a particular quantity associated with any physical system which counts the number of such internal states that it has, and this quantity is the entropy. The entropy of a system depends on the bulk parameters, for example, the temperature and pressure for a gas. For any given value of these parameters, it counts the number of internal microconfigurations that can give rise to them. The more microconfigurations consistent with the bulk parameters, the higher the entropy. The entropy of a gas measures the total number of ways the molecules can be pinging around internally, the vast number of ways that the gas's atoms can be moving, given a fixed bulk pressure and temperature. This entropy, the number of internal arrangements, increases with the temperature of the gas. Higher temperatures represent the case when molecules all go that little bit faster and carry that little bit more energy. Given all the many directions atoms can move in, there are simply more ways of moving faster than there are of moving slower. As an example of this, we can see that in the limit of the slowest movement of all, where speeds vanish entirely, an exactly stationary particle has only one way to move: the null motion. But can these concepts of thermodynamics, familiar from gases and rubber bands, really apply to black holes, one of the deadest objects in physics? Remarkably, the answer is yes. Even though there are no atoms whizzing around inside black holes, the thermodynamic concepts still apply. Just as we can talk about the temperature or entropy of a gas, so indeed can we talk about them for a black hole. This discovery dated back to the early 1970s, first suggested by Jacob Bekenstein and later fully developed by Stephen Hawking. Bekenstein had been the graduate student of John Wheeler. Discussing with Bekenstein, Wheeler had noted that when he mixed hot tea with cold tea, the overall entropy would increase in a manner that could never be undone. But if the mixed cups subsequently fell into a black hole, all evidence of this mixing would then vanish, as everything was swallowed up by the black hole into the fixed, unique black hole solution. And so this set Bekenstein thinking. Could it really be the case that the mixing between hot and cold tea would increase the overall entropy of the universe, but when the tea was thrown into the black hole, all the entropy of the tea would be lost? This seemed impossible. Indeed, the idea went against the almost sacred second law of thermodynamics, that the entropy of the entire universe must increase over time. This is one of the most treasured ideas in all of physics. Indeed, Arthur Eddington, famous for his work on relativity and nuclear fusion, was once quoted as saying, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observation, well, those experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." And so perhaps, thought Bekenstein, that just as each cup of tea had an entropy, and the overall entropy of the pair increased when the two were mixed, the same should be true of the black hole. When the cup of tea was thrown into the black hole, this would therefore just increase the total entropy of the black hole by 1 cup of tea. And it was this that led Bekenstein to the remarkable conclusion that black holes should indeed have an entropy, now called the Bekenstein-Hawking entropy. It was a truly bizarre discovery. But what did it mean? Which is the hottest black hole in the universe? Since the first discoveries of astrophysical black holes in the 1960s, a wide variety of them have been found. and their masses vary hugely. The heaviest known black holes, such as Phoenix A or Ton 618, are around 100 billion times heavier than the mass of the Sun. These are ultra-massive black holes at the centers of enormous active galaxies, capable of spectacular energies with their superpowered quasar jets. The lightest known black holes, however, detected as dark orbital companions to other stars or pulsars, are only a few times heavier than our Sun. Candidates for the lightest known black hole are the orbital companions of either the PSR J0514-4002e or the red giant V723. But bizarrely, these miniature black holes are a billion times hotter than the distant giants, although with a temperature a little more than 100 millionth of a degree. Hotter here is strictly relative. And so black hole temperatures are tiny, but they're not zero. Where does this heat come from? By the early 1970s, Bekenstein and Hawking had ascertained that black holes should have an entropy. Time's arrow, the second law of thermodynamics, continued to point forward. Fire particles at the black hole, and as they fell in, the entropy of the particles should be transferred to that of the black hole. The overall entropy of the universe would increase, and the laws of physics would be satisfied. Or so it seemed. For as he thought about it in more detail, Hawking's remarkable mind latched onto a problem with this picture. Imagine a hot gas falling into a black hole and being entirely absorbed. The resulting black hole, it was thought, should be cold, dark and compact. Nothing should come out. It seemed to be a zero-temperature object. In every other part of physics, when hot and cold objects are mixed, the temperature of the cold object is increased by the mixing. Yet here, the black hole seemed to remain inert, with a temperature of absolute zero. Indeed, this was the whole idea of a black hole. Not even light could escape. But this was where Hawking came in, with a striking and surprising idea. Doubling down on the notion of black holes as thermodynamic objects with an entropy, he proposed that black holes also have a temperature. Not a mathematical analogy to temperature, not a gravitational equivalent to temperature, but an ordinary temperature with exactly the same meaning as that we use to talk about ovens, boiling water, and the weather. The most exotic objects in the universe suddenly became eerily familiar. The classical laws of thermodynamics, dating back to the 19th century, relate entropy to temperature. In particular, they say that the temperature of an object is the inverse of the rate of change of its entropy with energy. This means that for a gas, when extra energy is injected, the number of gas configurations increases. By calculating this precisely, we can work out the temperature of the gas. But for a black hole, the entropy is actually set by the area of the horizon. In the simplest case of the Schwarzschild solution, this entropy behaves as the square of the mass energy of the black hole. Plugging this relation into the classical 19th century thermodynamic expression for temperature gives a striking result. The black hole must have a temperature, and this temperature changes inversely with the mass energy of the black hole. Big black holes are cold, small black holes are hot. The temperature of a typical astrophysical black hole in our galaxy, formed by a collapsing star and with a mass slightly larger than our Sun, is around a billionth of a degree. However, a much smaller, and hypothetical as far as we know, black hole, formed by compressing something like Mount Everest down to a point, would have a temperature of hundreds of billions of degrees, vastly hotter than the center of each of the largest stars. And so this unusual property means that black holes behave in a way opposite to our intuitions. A normal fire starts off warm and hot. As it gives off heat, it cools, and eventually there is little more than a small glow from the ashes, which eventually dies away to nothing. Black holes, on the other hand, become hotter as they give off heat. While the black hole starts cold, it gets hotter as it loses energy, eventually evaporating in a blaze of radiation. Strange, but characteristic of black holes. And so as we begin to unravel what this means, let's start with the simplest question. Why do black holes have a temperature? Hot Objects radiate. Place your hand near a fire or an oven and you will feel the heat without ever touching it. Indeed, precisely what it means for something to be hot is that it transfers heat to something that is cold. Place the two objects next to each other and they equilibrate at an intermediate temperature as heat goes from the hot body to the cold body. But black holes, we thought, were not meant to give out anything. Were they not introduced as voids in space which may eat and swallow and gobble, dragging all they consume towards some unknown singularity, but do not spit anything out? This, after all, is what the black in black hole refers to. They absorb light, but do not emit. And yet with the revelation that they had entropy, this was found to be not quite true. Indeed, if we could place our hand close to a black hole with a temperature of 1,000 degrees, the experience ought to be identical to placing our hand close to an oven with a temperature of 1,000 degrees. Just as our hand feels the photons from the oven striking our skin and transferring energy to the skin cells, which is then communicated to our brain via nerve impulses, so too our hand must feel photons from the black hole striking the skin and transferring heat to it. But where would these photons come from? For this to be true, there must be actual particles coming out of the black hole, not just falling into it. In the 1970s, this seemed absurd, completely inconsistent with the whole idea of what a black hole actually was. Could there really be particles coming out of a black hole? Remarkably, the answer was yes. Of Stephen Hawking's many contributions to physics, this result is the most important and the most enduring. The light that emerges from a black hole is called Hawking radiation, and it emerges with precisely the spectrum you would expect given the temperature of the black hole. Hawking radiation is theoretically well established and has been derived using many different approaches. But what all the approaches have in common is that they sit at the intersection of the physics of gravity, black holes, and quantum mechanics. And to understand this, we have to begin by thinking about Heisenberg's uncertainty principle, the idea that there is never a perfectly still vacuum in quantum mechanics. Nothing can be settled down completely. Or more accurately, nothing, empty space, can't be settled down completely. Imagine yourself close to, but just outside, the horizon of a black hole. If you were to cross the horizon, you would fall into the black hole and your fate would be sealed irrevocably. But instead, suppose you have a rocket with enormously powerful engines which are strong enough, just strong enough, to prevent you from falling into the black hole. The engines fire constantly and you remain just outside the horizon. Now imagine two beacons on the rocket, one on the side towards the black hole horizon and one on the side away from it. Light emitted from the horizon side beacon immediately crosses the horizon and falls, never to return, into the black hole singularity. Light emitted from the other beacon, however, pointed away from the black hole, succeeds in escaping the black hole and reaching deep space far away from it. This is similar to how Hawking radiation works. Contained within Heisenberg's uncertainty principle is the idea that in quantum mechanics even the coldest and emptiest vacuum is not empty. There is an intrinsic energy associated with this vacuum, and it's even possible to borrow this energy for a short period of time. The more energy you want to borrow, the shorter the time period you're allowed to borrow it for. This means that for very short periods of time, the vacuum can borrow sufficient energy to create, albeit temporarily, particle-antiparticle pairs. Provided these are rapidly reabsorbed back again into the vacuum and their energy returned, no harm is done to the laws of physics and the law of conservation of energy. Although this may seem strange, this is one of the key examples of the complexity of the vacuum in quantum mechanics. Nothing is far from straightforward. But sitting on top of this is the fact that this vacuum is not just empty space extending in all directions. Here, we are considering space just outside the horizon of the black hole, with the gravitational pull of the black hole always ready to take objects through the horizon. This vacuum comes with a direction, inwards, attached. What happens then, just outside the horizon, when energy is borrowed from the vacuum to create particle-antiparticle pairs, Or for particles like the photon, which is its own antiparticle, a pair of two back-to-back photons. Well, for a short instant of time, one can borrow energy to create a pair of photons. And for that same incredibly short instant, these particles can travel. And during this incredibly short instant, one of the pair crosses the horizon, the one-way portal, towards the singularity. And so the pair can no longer come back together. Just as our rocket, teetering on the edge of the abyss, fires photons both into and out of the black hole, so in a sense does the quantum vacuum. While one particle or antiparticle escapes off into infinity, the other falls into the black hole, and the borrowed vacuum energy now has to be repaid by the black hole. The net result is that one particle or antiparticle escapes, taking a tiny bit of energy with it, and this energy is repaid by the black hole losing a tiny bit of its mass energy. Detailed calculations confirmed Hawking's intuition that this process looks a lot like a hot oven radiating light. Hawking radiation is usually photons, as they are massless and can escape the gravity of the black hole. And so there it was. Stephen Hawking found that black holes were not black. But again, that was not the end. As ever with black holes, solving one problem introduced another. Because if you waited long enough, the black hole would eventually evaporate away entirely. There would be no interior of the black hole anymore. We can imagine a history that starts before the black hole is formed, with countless encyclopedias and databases falling in under gravity to create the black hole. Over time, the black hole evaporates, and at the end, there is a gas of particles heading out from where the black hole once was. And so what has happened to all the information that was once there? According to Hawking's calculation, the emitted radiation was that of a perfectly featureless thermal spectrum, which contained no trace of the original information. Where had it all gone? Could the information be reconstructed from the details of the emitted radiation? For 2 decades, this question was debated. In ordinary quantum mechanics, information is not lost. Were black holes like this, or did the unusual combination of gravity and quantum mechanics lead to some fundamental differences? Eventually, the answer came from an unexpected direction. The fact that the entropy was proportional to the area, not the volume, of the black hole. This was the first sign of a deep and subtle idea called the holographic principle, with huge consequences for the universe. Imagine you've dropped a book into a black hole. How you do this, somehow withstanding the brutal accretion disk and waves of radiation, is unimportant. The key thing is somehow you do. We can imagine the book falling until it reaches the central gravitational singularity at the very heart of the black hole, where any information that it carries is crushed utterly. And so, to understand whether or not the information is destroyed or survives, it seems we would need to understand this central singularity. What is the interior of a black hole like? Does information survive in a theory of quantum gravity? If we recorded the details of every photon emitted from the black hole through Hawking radiation, would we, in principle, be able to reconstruct the information? Most of the ideas that we've discussed so far, the existence and entropy of black holes as well as Hawking radiation, are, however exciting, still ideas which had been mostly worked out by the end of the 1970s. But over the following years, physicists have realized that the physics of black holes contains even more, the first hints of even deeper and stranger truths. In particular, the physics of black holes gave us the first glimpse of one of the most remarkable and shocking properties of gravity, the holographic principle. And it is this holographic principle that offers the best framework to think about what happens to the information lost to a black hole. To begin with, let's return to Hawking's formula for the entropy of a black hole. There's part of this which may not appear unusual, but is in fact the first indication of something groundbreaking. The entropy of a black hole grows with its area, and not with its volume. Physicists knew that the mass of a black hole is equivalent to the area of its event horizon, the geometric area of the surrounding spherically symmetric shell inside which nothing can escape. For the simplest Schwarzschild black hole, this horizon area depends simply on the mass of the black hole. But for spinning black holes, the expression of the horizon area was more complex and depended on both the mass and spin rate of the black hole. But by 1971, it was Stephen Hawking who had shown that whatever happened to a black hole, even including complicated processes which could extract angular momentum from a spinning black hole, actually slowing its spin, the horizon area would only increase. And in the second law of thermodynamics, it is entropy that can only increase. First Bekenstein and then Hawking realized that it was the horizon area, not the mass or the volume or the angular momentum, which behaved in precisely the way that entropy was meant to behave. When objects fall into a black hole, adding to the information and therefore entropy inside the black hole, the horizon area of the black hole increases. When two black holes merge, the horizon area of the product black hole is larger than either of its components. In complicated slingshots which could extract both mass and angular momentum from a black hole, the black hole mass decreases, but the horizon area increases. But why is this surprising? Black holes, as we have seen, are similar to gases in some respects. They are both thermodynamic objects with temperatures and entropies. Like hot gases, hot black holes give off radiation. However, there is an important and subtle way in which they are different. The entropy of any object is a measure of the total number of internal configurations that an object can have, a measure of the number of ways of rearranging the innards while keeping the external properties the same. For a gas, the entropy grows with the volume of the gas. If you imagine a balloon at a certain pressure, and we hold the pressure the same, the bigger the volume of the balloon, the more the number of possible allowed internal configurations of the gas. And so suppose we divide up the entire volume of the gas into lots of little blocks, little unit volumes of space. Each of these volumes could be either on or off. Perhaps on means a gas particle is in the volume, and off means it's not. With one block, there would be two choices. For 2 blocks, there would be 2 squared. For 3 blocks, 2 cubed. For 100 blocks, we multiply 2 by 100 times. Generally, the number of total configurations is 2 raised to the power of the number of blocks. And so, what is different about black holes? Well, for black holes, the Bekenstein-Hawking entropy depended on the area of the black hole horizon, and not on the volume. In terms of our picture of little blocks, each of which can either be a 1 or a 0, what this formula implied is that for black holes we could count the number of internal configurations by splitting the horizon area into many small little blocks. The counting process looks similar to what we did for gases, but only provided we do the counting on the horizon of the black hole, and not on the interior volume. And this is the holographic principle. The statement that, for many gravitational systems, the physics of the system is entirely encoded on the boundary of the system. The equations for gravity in the interior can be rewritten or translated into a different set of equations, which describes a non-gravitational theory that lives only on this boundary. Gravitational systems in a 3-dimensional space can be equivalent to non-gravitational systems on the 2-dimensional boundary. Gravitational systems in a 5-dimensional space can be equivalent to non-gravitational systems on the 4-dimensional boundary. Gravitational systems that live in a certain amount of dimensions are equivalent to non-gravitational systems that live in one less. One of the dimensions in the gravitational theory turns out to be redundant. This concept, also called today the ADS-CFT correspondence, is one of the deepest ideas in modern theoretical physics and is supported by a vast number of calculations. The key claim is that two separate mathematical theories, a gravitational theory in, say, 5 dimensions and a non-gravitational quantum theory in 4 dimensions, are actually identical theories, just written in very different language. Indeed, this has been mooted as a way to link the previously incompatible gravity and quantum mechanics, the holy grail of modern physics. And it was the Bekenstein-Hawking expression for the entropy of the black hole that represented the first inkling of this theory. But how does holography help with the information paradox? Where has all the information gone? Holography tells us that a gravitational system and its evolution can be described through an alternative, non-gravitational language. Suppose a gravitational system with an alternative, non-gravitational holographic description has a black hole, which forms and evaporates. In the context of the gravitational theory, we would worry that the information is lost. But in the alternative, holographic, lower-dimensional description, the process of formation and evaporation of the black hole occurs in a completely non-gravitational language. Here, it is simply an ordinary quantum mechanical system evolving in an ordinary quantum mechanical fashion, and there are no problems involving singularities or horizons. In such an ordinary quantum system, there is no question of information loss. The information is simply kept on the horizon, stored on a lower dimensional boundary. But still, even if we know that the information will be preserved, where is it exactly? The best answer yet is that it will lie in the details of the Hawking radiation. Although we may think of the radiation as being emitted from the black hole like an oven, all uncorrelated with each other, this is not quite correct. Instead, some physicists believe all the emitted photons are subtly correlated and entangled with each other. And it is here that lies the information that fell into the black hole. And so black holes are truly bizarre objects that challenge our very notions of what information and reality are. But what are they made of? Once they are formed and before they evaporate, are we able to say what a black hole actually is? For a gas, the microscopic configuration involves the locations and speeds of all the atoms that make up the gas. What is the analogue for black holes? Such a question is not easy and seemingly impossible to test experimentally. To access the innards of a black hole and see just what it's made of, our hypothetical rocket laden with future technology must first cross the black hole horizon. But of course, having done so, the rocket can never again leave the black hole, and so whatever nuggets of knowledge it may find can never be sent back to those scientists who remain outside. So the interiors of real black holes, many light years distant and with their interior hidden by the horizon, are beyond our current reach, both in practice and in principle. But mathematics can reach where rockets cannot. If we can't do physical experiments, the next best thing is to do thought experiments, or mathematical calculations of systems that do not precisely describe our real world, but instead describe ideal systems which share key properties with our real world. And so are there mathematical examples which capture some of the physics of real-world black holes, but have enough symmetry and control to enable us to do the calculation? In some cases, the answer is yes. In a famous 1995 calculation, Andrew Strominger and Kumran Vafa, both of Harvard University, studied a highly stylized example of 5-dimensional black holes in string theory. These black holes are mathematical. They exist in a world with one extra spatial dimension compared to our own. They were also very specific. They came with a package of extra symmetries and properties that do not hold for the ordinary black holes present in our universe. But for these extra special black holes, Strominger and Vafa were able to count and determine precisely the possible inner microstates that corresponded to a black hole solution. All the inner stuff that could make up the black hole. In this specific example, the answer involved extended string theory objects called branes. Counting all the ways these could be put together, they obtained an answer that precisely agreed with the calculation of Hawking. Although it was a calculation for a mathematical universe with extra dimensions and extra symmetries, this was still a calculation and a result. In this simplified situation, they were able to understand exactly the entropy formula for a black hole from a microscopic perspective and count up all the states that could make up the black hole. Unfortunately, however, for real-world black holes, we are still waiting for answers. What lies inside actual black holes, such as Cygnus A or TUN 618? We don't know, and cannot yet say what their internal microstates are or how their interiors are precisely captured by physics on their horizon. But ideas such as the holographic principle give us the hope that one day, perhaps, we will catch a glimpse inside. But maybe not until further surprises from these mysterious objects at the intersection of gravity, astrophysics, and quantum mechanics. And so still, almost 300 years after they were first proposed, nothing in the universe is as mysterious as a black hole. You've been watching the entire history of the universe. Don't forget to like and subscribe, and thanks again to MyHeritage for their support. Use the link below to try their 14-day free trial. Thanks for watching, and we'll see you next time.